Concrete hollow bricks are commonly used in construction because they are lightweight, economical, durable, and easy to install. Compared to solid bricks, they reduce the overall weight of structures while still providing sufficient strength for walls in residential, commercial, and industrial buildings. In line with sustainable construction, this study explores the use of agriculture waste as a partial replacement in building materials. Rice husk ash (RHA), which is produced from rice husk, is used to replace 3% of natural sand in the production of hollow concrete bricks. This helps reduce waste and conserve natural resources. The objective of this study are to produce sustainable hollow concrete bricks, test their physical and mechanical properties, and evaluate the suitability of using 3% RHA as sand replacement in bricks production. The main materials used to produce hollow concrete bricks are cement, sand, coarse aggregate, and water. In this study, rice husk ash was introduced as a sustainable material to partially replace natural sand. RHA is an agricultural waste produced from burning the rice husk. It has fine particles and a lightweight structure, making it suitable for use in concrete mixture. The use of RHA helps reduce agricultural waste and decrease the consumption of natural sand resource. In addition, RHA contains a high amount of silica, which can contribute to the bonding process in concrete and potentially improve its properties. Therefore, 3% of natural sand was replaced with RHA in the production of hollow concrete bricks to evaluate its suitability as a sustainable construction material.
Concrete mix preparation. The concrete mix was prepared by partially replacing fine aggregate with rice husk as RHA at a replacement level of 3% by volume. Before mix, the RHA was dried and sieved to ensure uniform particle size. The required amount of fine aggregate was reduced by 3%, and equivalent weight of RHA was added as the replacement material. All material were weighed according to the design mix proportion. The dry material, including cement, coarse aggregate, fine aggregate, and RHA, were first mixed thoroughly to achieve a homogeneous distribution. Water was then added gradually while mix continued until a consistent and workable concrete mixture was obtained. Brick fabrication process. The brick were cleaned thoroughly and a thin layer of oil was applied to easy remove of the specimen. The prepared concrete mixture containing of 3% of RHA as a partial replacement for fine aggregate were placed into the mold until it was nearly full. The concrete was compact manually by hand to climatic air improve the density of the brick. The surface of the specimen was leveled manually to ensure that it was flush with the top of the mold. The mold specimen were left undisturbed for 24 hours before being removed from the mold. After demolding, the specimen were labeled for identification and cured in water for 7 days before testing. The specimen were kept moist throughout the curing period and were not allowed to dry before the testing process. Compressive strength test. The compressive strength test was conducted to evaluate the mechanical performance of the concrete brick containing 3% RHA as a partial replacement of fine aggregate. The specimen will test after 7 days of water curing to determine the development of strength over water. Before testing, the specimen were removed from the curing and excess water on the surface were removed by wiping and air drying under sunlight. Each brick was placed centrally in the compressive testing machine to ensure a uniform distribution of load. The load was then applied continuously until the specimen failed. The maximum load required feeder was used to calculate the compressive strength of each specimen. The result obtained at different grades were compared to evaluate the effect of incorporating 3% RHA on the strength performance. Evaluation. The result obtained from the compressive strength were required and analysed to evaluate the performance of concrete brick containing 3% of RHA as a partial replacement for fine aggregate. Adding 3% RHA as a partial replacement can affect the strength of the brick. RHA can react in the cement and help from extra binding material because RHA have high silica, which can make this brick stronger. However, if the RHA is not mixed properly, it can create empty pore and weak area inside the brick, which can reduce its strength. Overall, the results show that RHA has the potential to improve strength, but the difference in the result may be caused by inconsistent mix of our preparation. More tests with better control and more samples are needed to get more accurate and reliable results.
Now, let's move on to the mix design and compressive strength results. Based on the first image, our group calculated the concrete mix using a target mean strength of 43.12 newtons per square millimeter. The main difference in our mix is that we replaced 3% of the fine aggregate or sand with rice husk ash. This was done to make the hollow bricks more environmentally friendly. The total mixed volume was 3.197 times 10 to the power of negative 3 cubic meters, which was enough to produce 2 hollow bricks. After casting, the bricks were cured for 7 days before the compression test. Both bricks weighed 1.9 kg. Specimen 1 withstood a maximum load of 137.24 kilonewtons and achieved a compressive strength of 6.86 MPa. Specimen 2 carried a higher maximum load of 179.18 kilonewtons and achieved a compressive strength of 7.67 megapascals.
2 hollow concrete brick specimens containing 3% rice husk ash were tested after 7 days of curing. The compressive strength were 6.86 megapascal and 7.67 megapascal, showing consistent results. Overall, the brick still achieved satisfactory early age strength, indicating that the addition of 3% rice husk ash does not significantly affect concrete performance. From a sustainability point of view, rice husk ash helps reduce agriculture waste and decreases the use of natural sand, supporting more sustainable construction practice. In conclusion, 3% rice husk ash can be used to produce hollow concrete bricks with consistent compressive strength and environmental benefit.
In conclusion, RHA concrete brick can withstand substantial load after 7 days of curing. Variation between specimens show the need of better material preparation and consistency. The study successfully produced sustainable hollow concrete brick using 3% RHA as partial sand replacement. Agricultural waste can be effectively used in sustainable construction material. Proper material selection, mix and curing are important to ensure good brick quality. For limitation, possible measurement error and uneven mixing of material, different in curing condition affect result consistency. To improve that, we have to ensure accurate calculation and weight of material, improve mixing to achieve uniform distribution, and proper compaction to remove air void and improve strength.
One of the advantages of this project implementation is that rice husk is an agricultural waste material, so it is much cheaper compared to natural sand. Even though we only replace 3% of fine aggregate in this project, it still reduces the total amount of sand required in the mix. This means lower material consumption and potential cost saving. If this is applied in large-scale brick production, the cost reduction can become more significant. It also helps reduce waste disposal costs because rice husk is reused instead of being burned or thrown away.
Next advantage is enhanced environmental sustainability and waste management. Enhanced environmental sustainability by reducing the volume of waste sent to landfill. Lower environmental impact and carbon emission associated with conventional waste management and material production. Reduce agricultural waste by replacing rice husk ash (RHA) instead of disposing it, and support eco-friendly construction practice through the incorporation of renewable and recycled resources.
The third advantage is supporting material innovation. By replacing 3% of sand with rice husk ash, we can utilize an agricultural waste material as a supplementary material in hollow brick production. This shows that waste materials can be successfully incorporated into construction materials while maintaining good brick performance. In the long term, this approach encourages the development of more sustainable and innovative building materials for the construction industry.
For the last advantages of this project, we can understand that rice husk ash or RHA potentially enhances the brick performance in several ways. Its high silica content improves the bonding between the cement paste and aggregates, while its fine particles help fill small voids in the mix, creating a much denser and more compact brick structure. This improved density may help maintain or slightly increase compressive strength, and it also enhances the durability by reducing water absorption and improving resistance to weathering over time.